Hello, I'm Doug. This talk is titled Gauge Games in a Unified Field Theory, a talk I gave to the fall APS meeting in Durham, New Hampshire. Gauge games impose very simple rules that are incredibly difficult to solve on any reasonable proposal. I will describe how the standard model actually solves these constraints. I will describe the Maxwell action because it serves as a springboard for my proposal, which is a collection of variations on the Maxwell action. I will show how two of these working together actually are able to solve the very difficult constraints imposed by gauge transformation properties. Before I go into this slide, I will describe a little bit about what an action is. An action is an integral over space-time of all the ways that energy can be exchanged per unit volume. What one then does is look for ways to vary this action such that the integral actually doesn't change over arbitrary amounts of time. When you find such a thing, such a symmetry, then you found something profound, because it means that that quantity eventually will be is conserved. So if you can vary an action with respect to time, then energy is conserved. If you can vary the action with respect to location in space, then momentum is conserved. And this slide describes when the action is invariant under a gauge transformation, it means several things. First of all, that the speed of particles in the field is c, the speed of light. That there is no scalar field. And you are free to choose the gauge. Now, what does that mean? Well, let me do this by giving you three well-known examples from electromagnetism. The Coulomb gauge has del dot A equal to 0. The static gauge has the time derivative of phi equals to 0. And the Lorentz gauge has the difference of these two being equal to 0. And one chooses one of these gauges in order to make solving a problem a little simpler. But what is key is that you're utterly free to make your choice, and it won't have any consequences to the physics, just to the math that you go through. So when an action is not invariant under a gauge transformation, it means basically the opposite. That particles are going to be traveling at less than the speed of light c. That there is a scalar field, and that the gauge is somehow determined by the physical conditions. Now, what's a real riddle is that both are needed for the very same action. Consider photons interacting with massive charged particles, because all charged particles have mass. Well, those photons, they're going to have to travel at the speed of light c. And those massive charged particles, they are going to have to travel at less than the speed of light c. And contradictions like this turn out to be common in theoretical physics. Perhaps the most famous is the wave-particle nature of particles themselves. And so this tells us that this actually is what we should expect, this sort of contradiction, and that we have to come up with a way to deal with it. So the current answer to the riddle is the false vacuum of the Higgs field. The standard model action has the symmetries U1, SU2, and SU3, and these correspond to three different forces: electromagnetism, the weak force, and the strong force. And it also corresponds to conserved charges for the electric charge, the weak charge particles, and the strong charge particles, all those quarks and whatnot. As long as all of those things have no mass. That's the way the math works. So the Higgs mechanism is a way to get around that very serious problem. And it introduces the Higgs field, which is a false vacuum that spontaneously symmetry breaks, and it's that spontaneous symmetry breaking from this false vacuum that gives mass to so many fundamental particles. Actually, mass comes in a whole bunch of other ways too, but this one is really important for quarks and whatnot. Now, I actually consider this to be a trick, in the sense that it doesn't seem reasonable to me that, given the crazy distribution of matter we have in this universe, that the Higgs field magically lines up absolutely everywhere it needs to. In the vacuum of space, there's not much matter, but there's got to be exactly the right amount of Higgs fields out in that place where matter is quite scarce. And then we have an enormous range of densities, from the Earth to far denser in the Sun, to neutron stars, to things that are considerably more dense than neutron stars. And in all those cases, the Higgs field has to be in lockstep, or otherwise mass charge would not look as perfect as it always has. But if you don't have a counter proposal, then the Higgs really is the only thing that adds mass without breaking these symmetries. Because if the symmetry was broken, then electric charge wouldn't be conserved, or the weak charges wouldn't be conserved, and that would also be really, really not good. So not good that the LHC, that's the Large Hadron Collider, its job is to find the Higgs. So I'm going to start down the path to my unified field theory proposal, or hypothesis, by starting with the best field theory that there is, and that would be the Maxwell action. We have this antisymmetric rank 2 tensor contractions, and that might actually look a little bit scary. But when you kind of crank through this algebraically, what you end up with is a little bit more familiar. You end up with b squared minus e squared. So the magnetic field squared minus the electric field squared is the scalar that ends up being the Maxwell action. And then by taking various derivatives of this, you can actually, if you put it right in the Euler-Lagrange equation, you can derive the Maxwell action. And I have another talk about that. And if you can ever do that with paper and pencil, it's really one of the best calculations you'll ever do in your life, because it's just so elegant the way it all falls out. Other variations can give you the stress energy or a force equation. So I'm going to create variations on the Maxwell by rewriting them with quaternions. Quaternions are a 4D division algebra. That might mean nothing to you. Well, real numbers are a 1D division algebra. Complex numbers are a 2D division algebra. There is no 3D division algebra. One then gets to the quaternions, which are these 4D things. So you can basically add, subtract, multiply, and divide them. So I write out this action, and I don't need any Greek letters. So that is really the reason everyone should do this. Oh, no, actually not. But let's just evaluate that very first one, the del A. What you get in the scalar term is a gauge term. In fact, you get the time derivative of phi minus the divergence of A. And then you get minus E plus B. Now, when you reverse the order of those two, you get the same gauge term, but you get minus E and then minus B. The reason it flips its sign is because the B field is a curl, and changing the order of that flips the sign of a curl. Now, because these are quaternions, now you couldn't do this if these were tensors, but they're quaternions, so you can multiply these two together, and of course you end up with B squared minus E squared. And you actually do get a 3 vector out of it. You get, it's called the pointing vector, and so that is like physically significant, but you can also like zero that out for the action here and end up with identical terms in the scalar, which means that you get identical field equations, identical whatever you calculate. So all we've done here is essentially change notation, no big deal. But what I want to point out for this talk is the stuff in yellow, that we've got these, this is how the expression is symmetric under gauge transformation, or sorry, invariant under gauge transformation, because we're subtracting away the terms. We've got, if you put whatever d phi dt in there you want, put in whatever del dot A you want, it's going to be subtracted straight away from the action, so therefore it's not going to change anything. Now, we're going to do real variations by putting in the standard model symmetries. This can be done because quaternions can actually represent the relevant groups found in the standard model. SU2 is in fact called a unit quaternion, and it can be represented as the exponential of A minus A star, which basically gives you the 3 vector in there, and that always has a normal 1. And wherever there's an A in there, just put in that exponential, and you'll have the SU2 symmetry, and therefore you can vary this thing with respect to that, and it won't change. And that's great because it means there'll be these 3 conserved charges. Now, you can also do electroweak symmetry by just multiplying that exponential by A over the absolute value of A. And here's another one of those wonderful physics contradictions, in that U1 is an abelian group, which means it doesn't matter which side you write it, what order you write things, whereas SU2 is non-abelian. And yet you've got to have the two playing nicely with each other. Well, in this case, people say, well, quaternions, they really aren't into commuting with each other. Well, actually, they're into commuting with themselves, which is what happens here. I can write that A over the absolute value of A on one side or the other. Doesn't matter. That's the behavior of an abelian group. Now, if we go with a B sort of thing, well, then we get into trouble, and that's the non-abelianness kind of we characterize as being in the SU2 part. Okay, so now we move on to the strong force, and if we just took 2 electroweaks and multiplied them together, well, we would get a third element of the electroweak, but by putting that conjugate in there, I get a different multiplication table. So I have this thing which obviously has a normal 1, and obviously involves 8 little independent elements, and so I think that this may be a way to represent SU3, but just not a very popular way. All right, so we've got the symmetries covered for EM, the weak force, the strong force. How are we going to get out to gravity? Well, before we go there, let's think a little bit about what is known experimentally about gravity. And one of the things that is known is that you can describe the effects of a weak gravitational field with a metric that changes. Now, a metric is symmetric, And so if that symmetric thing changes depending on where you go in the gravity field, then that change too will be symmetric. And you say, but quaternions with that curl and cross product kind of thing, they're probably not going to be able to describe that kind of symmetric change, which is exactly right. Quaternions cannot do that trick. So we are going to make another type of variation on the Maxwell equations by using hypercomplex multiplication for the gravity action. Quaternions are unpopular, but hypercomplex numbers are like a freak show. I mean, nobody uses them. But I need them. Okay, I need their properties. All right, so what are their properties? Well, they're just really, I think of them as like California math. They are super positive. Okay, I squared equals j squared equals k squared equals plus 1. There is no negative sign in the house. And in fact, that actually creates a problem. I have to throw in conjugate operators in here to throw in a few minus signs. All right, so if you have this super California positive kind of math going on, but you got the same kind of operators, the same potential in there, you're going to end up with all the same terms. It's just that you're going to have like sign differences here, there, and whatnot. And so the field equations are very similar to Maxwell with sign changes. So let me give you a critical difference. Now take Gauss's law in EM. In a static case, you have rho equals minus del squared phi. And what that means actually is that like charges repel, which is true of like charges in EM. But with the sign flips that go on in here, when you take that action and you put it through the Euler-Lagrange equation, you end up with a Gaussian law that's rho equals positive del squared phi, which happens to imply that like charges attract, as happens for gravity. Now, there's a lot more things that have to be done to prove this is actually a reasonable action and then resulting field equations. But for this talk, I just want to focus on the fact that this is going to be invariant under a gauge transformation because of that subtraction. In fact, it's subtracting away the same darn term. It's subtracting away the time derivative of phi minus the divergence of A. Okay, this equation really is independent of the stuff I've been saying about EM, the weak force, and the strong force. There's no kind of formal link between the two. So let's see if we can kill several birds with several stones and actually subtract this gravity expression from the Maxwell one without doing the gauge symmetry kinds of subtractions that we had done internally to the EM and gravity expressions. So what we end up here is an action where we see the terms for EM, and we now know that that is sensitive to gauge transformations. It will change if we change gauges. And the same is true of the gravity stuff. It is going to change if we change gauge. However, we've got that minus sign in there. So that says overall, it really doesn't matter because the gauge for the EM part nicely cancels out the gauge for the gravity part. And so we've done all of this without using the Higgs mechanism, without postulating this Higgs field lying under everything, no matter how dense it is or non-dense it is. It's just the way the algebra works out that each one of those separately is not symmetric under a gauge transformation, and yet together they are. So we actually do predict that the LHC will not find the Higgs. Now, since they have an $8 billion bet, we will bet that they keep on looking for a very long time, and if this proposal is correct, they will never find it. But I'm going to give you a bonus slide because it's almost a legal requirement that anytime you predict, write out an action, you're obligated to apply the Euler-Lagrange equations and see what the field equations are that result. And what's really stunning is that the field equations look like Newton's second law. Okay, so this really is standard stuff in the sense of it's standard math machinery. You've got a scalar there, you do the Euler-Lagrange, and you get this first field equation, and well, it's got 3 terms, and you say, well, look, I know it's symmetric under a gauge transformation, so why don't I just use that Lorentz gauge, and you get rho equals the second time derivative of phi. I mean, that was so stunningly simple. I had to take the missus out for a dinner in a very fine French restaurant in Acton, Massachusetts. Of course, I kind of go, oh, hold it. Isn't that maybe too simple? I mean, I had that worry. And then I said, no, now hold on a second. I know the action that was used to generate it. I know how to look into that action and literally see U1 symmetry and therefore electric charge conservation, to see SU2 symmetry and therefore the weak charge kind of conservation, to see the strong force charge conservation symmetry and therefore charge conservation, to see this kind of hyper-complex algebra which is kind of needed in order to describe symmetric changes in metrics that has been confirmed. So it's like nature works. Nature is so dense with information. It's kind of just really, really nice that this unified field equation just really is that incredibly elegant. Thank you very much.